All right, next up we have Samuel. He is going to be giving an incredible talk on iMessage exploitation. Super intriguing topic. Welcome, a warm round of applause all the way from Switzerland.
Okay, I'm ready. Cool. Yeah, thanks everyone for coming. Having a great time. Hope you're also enjoying the conference as much as I am. Yeah, I'm going to be talking about iMessage exploitation. So I guess most of you are more or less familiar with iMessage. It looks like this. It's Apple's messaging service. So in terms of like what you need is just the phone number or the email address or the Apple account to be able to send messages to someone. From a security point of view, it's pretty interesting because it's default enabled. So like any iPhone that's registered with an Apple account can be like reached over iMessage. It has something listening to incoming messages. So this is like default, no interaction attack surface, which makes it super interesting. And so Natalie and me set out to do some security, look for security vulnerabilities in it sometime last year. And yeah, I'm going to talk about what we found. So in terms of wire format, like what actually gets sent over the network, this is how it looks like. It's p-lists. This is the like textual representation, but it's really binary p-list that's being sent. I guess most of these keys are kind of self-explanatory, like P is participants, T is the text content, V is probably conversion. Interestingly, there's also some like XML in there, which seems to be used like it's not HTML. It looks like HTML. It's pretty complex, and it had a couple of bugs in the past. So Ian Beer found some, for example. And so now what this means is that this entire serializer is now zero-click attack surface, because well, it's included in the plist, and you can send these iMessages to any phone with an Apple account, and it will deserialize these archives. So when we found that this looked like the biggest attack surface immediately, so we spent pretty much all of our time looking at this. Yeah, again, it's a bit more about the serializer. So it does support quite a lot of things, like all the common dictionary array container things. It supports some weirder things like arrays of C strings also, I don't know why. It even supports like cyclic references, and we'll get to that in a minute. And yeah, I would recommend reading Natalie's blog post. It's really good on like this kind of attack surface. And on the bottom here, you have some example code how this archiver works from the API. So yeah, you can restrict like what it will unarchive. So in this case, this is saying like only allow dictionary strings, data, number, and so on. But it's more complex because actually it allows subclasses also. So this looks like it would only allow NS dictionary, but really it also allows like NS something dictionary because it inherits. So like it respects inheritance hierarchies. So the attack surface is much bigger than what this would suggest. Yeah, so this is the bugs we found pretty much on the left. It's, I don't know, 10 or so. I think they were all, maybe apart from like one or two, they were all in this NS unarchival thing. The particular bug that I then exploited is 1917, just because it looked the most, the nicest to exploit, I guess. But I'm fairly certain some of the others could have been exploited in a similar way. Yeah, timelines like reported July 29th. The first thing Apple did, which was really good, is with iOS 12.4.1, they pushed a mitigation that kind of blocks a very large part of this attack surface in iMessage, so that was really a good move. And this change would have made all of our reports non-remote issues. So this was a pretty good thing to do. And then, so after that point, all of these bug. So this bug was only local attack surface because this like unarchiver thing is also used locally over XPC, and then it was fully fixed in iOS 13.2. Right, so let's take a look at the bug. It's kind of interesting. It's like a cool Objective-C bug, Objective-C memory corruption bug. What we have to know first is what a shared key dictionary is. So it's a subclass of NS dictionary, and that's why it can be decoded. Yeah, it's a dictionary, so what it's supposed to do is like map keys to values. So here's, in reality, this is Objective-C, right? But I've like made it pseudocode, Pythonish pseudocode, I guess. So the lookup for this sheet care dictionary, it works basically by using a key set to get an index, and then using that index to index into some array, right? So every sheet care shared key dictionary has a values array and a key set. Now the key set is the more interesting thing. So the lookup is kind of something like hash the key, take that hash and use it as index into some rank table thing. And then whatever that gives you, use that as an index into a keys array. And then do a key comparison, and if that matches, then we have an index. Okay. The very important invariant here is that there's this num key value that says like how big is the keys array, and this has to be consistent, right? So if num key is not equal to the like actual length of the keys array, then we have a problem, because then like this one line here will just exit out of bounds. So keep in mind, this is really important. Num key has to be equal to keys, the length of the keys array. And then the other interesting thing is that these key sets actually form a linked list. I don't really know why, but it has support for like linking multiple shared key sets together. And if the first key set doesn't have the right key, it can go to the next one, again, try to find the key, and it will keep doing that until there is no more key set in the list. Okay, so this is roughly how these things work. Let's take a look at the vulnerability. So this is the decoding code for a shared key set. So this is like when you're sending a serialized shared key set, then this code will be run to deserialize it. And it looks pretty decent. Like it's just taking out these fields, right? It's taking out num key, it's extracting rank table, and so on. And then in the first if, it's checking this invariant, right? It's making sure that the length of the keys array is equal to num key, and if not, it's failing. And then the last thing it does is it kind of does a sanity check, where it's making sure that it can look up every key that it's supposed to contain, right? So this is just like, yeah, making sure it actually works. So let's see how this is broken. So I have this animation. We start from an empty shared key set, which is like all 0. This is how Objective-C allocates stuff. It's like everything is nulled out. And now we start filling it with, like we control all these values. So we can fill it with whatever. So we fill it with like really large num key value, a rank table of size 1. Okay, so you already see like this can't be right. Num key and rank table is well, no, sorry, I'm making things up. Rank table is fine. Keys is what has to be, what would have to be gigantic, right? But let's see what happens. So next thing we do is we decode a sub key set, right? And at this point, the whole process starts over again. So again, we like start from the top. We start decoding this second shared key set. Again, do this. And now we make a circle, right? So here we say the sub key set of the second one is actually the first. And now this isn't like supposed to be that way. But it does work. So the key unarchiver has like logic to handle this. And so yeah, it just like works. We have this cycle now. We decode keys. Now this is fine, right? So the second key set looks kind of okay-ish. And now we get here, and now we try to look up all these keys. And so in this case, the first key we like the lookup fails because like the rank table index is too big. It like doesn't work. So it recurses, and it actually goes to the first shared key set and tries to look up things there. But at this point, the first shared key set isn't fully initialized. Like, it hasn't reached the sanity check. It hasn't reached this first if statement. And so the num key value is completely controlled. It's not safety checked. And so in this case, it will actually just like index with hex 41, 41, 41, 41 into this keys array that's null pointer. And so it will access like completely controlled memory and do something with that. And so this is exactly our vulnerability. So I have these checkpoints just to like get everyone back to where we are. So next question is, what kind of exploit primitives does this give us? So again, this is the lookup code that I've shown at the beginning. When we trigger this bug, the keys array is null pointer and index is controlled. And so what it's doing is it's accessing like an arbitrary address, okay? But then it's also gonna treat that as an Objective-C object and call methods on it during the string comparison. Like, it's gonna call isNSString, for example. It's also gonna call dalloc, the destructor on it. And so the primitive really we have is like, we can take an arbitrary address and treat that as an Objective-C object, and then get some methods called on it, right? And so that's it. And so the question now is, well, how do we exploit this? So for this, we need some Objective-C internals, which seems pretty fitting for this conference. So here's some very simple Objective-C code. It's just making some Bob object, whatever that is, and then calling a method on it. And so if you do this, like in memory, how it would look like is you have the Bob instance, which is created by the like Bob alloc and init call. And the Bob instance has a pointer to its class. So there is a class object in memory. There's one like Bob class in memory. And the instance points to that with its like ISA or ISA, I don't know how to pronounce it, field. So that's pretty much just the pointer to the class. And so when we call a method on that instance, what the runtime is going to do is it's going to have it from the instance go to the class, and then the class has this method table, and then we're calling do something. So in the method table, it looks for the implementation of do something, and if it finds it, it's going to call it. If it doesn't find it, it will go to the like super class, and if it still can't find it, it throws an exception. Okay, so some small Objective-C internals. What does that mean for our exploit? Well, what we want is like gain code execution. So we know that due to our bug, it will call like Objective-C methods on something we control. So what we want to do is fake an Objective-C object, fake an Objective-C class, and then we can control code pointers, right? Because if it's calling isNSString, for example, if we fake all these data structures, it's going to call or jump to address 3133770. So that's going to be our goal. The problem is for that we need a couple of addresses, as you can see here. Like, we need to put these objects somewhere, and we need to know like code addresses. And here's where ASLR comes in. So very common, widely used exploit mitigation, which randomizes all the addresses in a process, right? So before ASLR, everything, like every library was always mapped at the same address. With ASLR, everything is now shifted, and so we don't actually know where anything is in memory, right? And so, checkpoint here, the first thing we now need to do is we need to break ASLR, because we need these addresses to like fake objects and jump to code addresses. And so here again, these are the addresses we need to know. And we can divide them into two categories. So one is heap addresses, this is where our objects will live, and the other is library addresses. And we'll deal with both of these now. So the heap address is actually really easy because there's something called heap spraying, which is like a very old technique, 15 years or so, probably older. The idea is very simple, just allocate lots of memory, and then eventually like some known address will contain the allocated data. On the right you can see some code which should just do that on iOS. It allocates 256 megabytes. So you can just try running this in an app, it should work. So allocating 256 megabytes of memory, and then this address hex 1170 or whatever it is, does contain the allocated data. So that's pretty easy, and now what this means is we can like spray 256 megabytes, and then we have our faked objects at this address. Okay, so this problem is taken care of. We do have another address which we need, the library addresses. So for that, some more iOS or macOS internals, it's like the same thing used on both platforms. The DYLD shared cache. So that's a pre-linked blob of pretty much all the important system libraries on iOS. It's gigantic, it's like a gigabyte or so in size. And it has a couple of interesting properties for like security researchers. So first thing is it's always mapped between hex 1870 and 2870. So there's only a 4 gigabyte region in which this 1 gigabyte thing will live. It's randomized, the like granularity of randomization is hex 4000. That's large pages on iOS. But what's most interesting is it's actually mapped at the same address in every process on the same device. So randomization is per boot and not per process, which means that if we know where the thing is mapped in one process, we know where it's mapped in all the others on the same device. So this will be really important. So kind of this is how the situation looks now. We're looking for the shared cache. We know it's between these two addresses, and so really we just need to know this offset from the start. So suppose we had, I hope you can read this, suppose we had this like Oracle function, which we could give an address and it would tell us, is it mapped or is it not mapped? So just assume we have this, we'll see where it comes from in a second. If we have this, then we can solve this easily, because then all we would do is like step linearly between these two addresses, and then the first time we find an address that's mapped, then we know we have found some address in the shared cache, and then we just do a binary search and like figure out where the start is, right? So like in this case, the linear search would find maybe these two addresses that are not mapped, and then we would find the next one that is mapped, and then we do a binary search between the last that's not mapped and the mapped one. Okay, and then we have the base address. So this would be really easy if we had such an oracle. Question is why or where would we get this from? And so another iMessage feature, or really like this is a widespread messaging feature, are these receipts. So there's two kinds of receipts. There's delivery receipts and read receipts. You can kind of see if you ever use iMessage, you probably recognize these message statuses here. So here I have 3 different messages with 3 different states. The first one was read, the second deliver, and the third nothing. And so what that means is for the first message, the sender got back 2 receipts, a delivery and a read receipt. For the second message, the sender got back only a delivery receipt, and for the third message, the sender didn't get back anything yet. And so this is pretty interesting because these delivery receipts are sent automatically by the receiving device back to the sender. And so if we look at when they are sent, it's even more interesting. Here's pseudocode for the handling of iMessages in this one daemon. And so like it's parsing the incoming data as a plist that we've seen. Then it's doing this unarchiving. This is where our bug would trigger. And only then is it sending these delivery receipts. And so what this now means is that if during the unarchiving we crash, we will never see a delivery receipt. And if we don't crash, then we'll see a delivery receipt, right? So now we have like this 1-bit information coming back. Did it crash or did it not crash? And this is exactly what we need for this oracle. Okay. So the vulnerability that I'm exploiting here, it doesn't yield this perfect oracle function. Like it doesn't let you ask, is this address mapped or is it not mapped? It lets you ask a different question. It's something like, is it mapped? And if it is mapped, is it 0 or does it have some bit set or whatever? It still works, but it's a slightly small bit more complicated. But do check out the blog post if you're interested. But yeah, the rough idea still works. It's still kind of a binary search thing, and it takes only like 20 to 30 messages to do this like probing, this binary search thing, and so on. And so it takes less than 5 minutes. You will see it hopefully in the demo later. Right, so again, this is kind of the summary of the ASLR bypass. There's 2 phases. The linear scan, where it just like goes in 128 or so megabyte steps until it does get back a delivery receipt, where it knows, okay, I found something that's mapped. And then there's this binary search phase. The CPU feature meant to stop or like at least make binary exploits more difficult. The idea is to store cryptographic signatures in top bits of a pointer. So you can see the example in the bottom. You start from a normal code pointer, and you realize like the top bits are all 0 because there's nothing mapped there. Then you sign that, and you do this like, for example, during process initialization. And then so the signing is like computing some cryptographic signature, and then you store the signature or like parts of it in the top bits of the pointer. And then when you actually use this pointer to jump to some code, you authenticate it, right? And so this authentication, what it does is like recomputes the signature, compares it with the one in the pointer, and if it doesn't match, it will pretty much just crash your process. And so it is used to ensure more or less control flow integrity currently. It can do more, it probably will be used to do more stuff. And the key idea here is the attacker doesn't have the key, and so the attacker can't compute these signatures. Brandon did some really good research into this and wrote blog posts, so if you're interested, go check out those. Anyway, what we need to know now is we're just going to assume we can't fake any of these code pointers because we don't have the key. And so our current exploit attempt or approach doesn't work, right? It involves faking a code pointer, it involves faking these classes which have code pointers, so that doesn't work because we can't fake these pointers. So let's go back here. Go back to Objective-C internals. This is the same slide I showed at the beginning, right? The instance pointing to the class. What we can do now is take a look at which of these pointers are signed and which ones are not. And so the code pointers in the class, they are obviously signed. But what is not signed is the ISA pointer. So the pointer from the instance to the class. That's still a raw pointer. I guess the main reason right now is that this pointer actually uses the top bits to store other parts of information, like it stores a ref count there, so it just can't store this signature right now. Cool. So again, the ISA pointer is not protected. What this means is that while we cannot fake classes, what we can do is we can still fake objects and make them like point to legitimate classes, because again, this ISA pointer isn't protected. And so we can, with that, get pretty much like existing functions or methods called, right? Because we will make an instance of an existing class, and so this class will have correctly signed pointers. And so if we call methods on that fake object, it will like call the legitimate Objective-C code that's in the process. And so, for example, this lets us call any dialog method in the process. Okay, so this is where we are. So for the pack bypass right now, we can call dialog on some class. So the thing is, yeah, we can call dialog, but what we want to call is some arbitrary Objective-C method, right? We want to launch a calculator because that's what everyone wants to do. And so we really want to do this method call at the bottom, like the UI application launch something, blah, blah, blah. So the question is, how do we get from being able to call some dialog implementation to calling this? And we need more Objective-C internals. There is some really cool class called NSInvocation. It's basically like a bound function call. It lets you, it's an object that lets you set like the receiver and the method to call, and then lets you set all the arguments. And once you call the invoke method on this object, it will do this method call on your target, right? And so if you wanted to call this launch application with identifier method, the NS invocation, this thing as an NS invocation looks like that, right? So you make an NS invocation object, you set the target, you set the method, you set some arguments, and then you invoke it, right? So why is this useful? Well, let's assume we have a dialog function that calls invoke on a controlled NS invocation. If we have that, then we could just like fake an NS invocation and get its invoke called, and then we would get a completely controlled method called. And so the way I did it is I wrote some IDOC-Python, which you can see here. It's really just these like, I don't know, 7 or so lines of code, which find every dialog implementation in the process, and then decompile that. And so then I have a like list of, I think it's a couple 10,000 dialog methods, and then I just grab for invoke in those, right? And this turned up at least one. So here's this MP media picker controller class, has a dialog, and what it's doing is besides other things, it's calling the invoke method on one of its fields. And of course, since we completely control this object, we control all the fields, and so we can like make field hex 350 point to some, again, completely controlled NS invocation. Okay, and so this finally lets us now call arbitrary Objective-C methods through NS invocation. Okay, what about sandboxing? So we can run Objective-C code, but are we sandboxed? So on the right side, you see the most important daemons handling iMessages. It starts with APSD, Apple's push services daemon, goes to this identity service daemon, etc. IMagent is doing most of the work, and then Springboard is showing these notifications. Right? Springboard is like the main UI process. And those with the red border, they are sandboxed, but Springboard isn't, like it's a system daemon kind of. It's really important. It has to do all kinds of things, so it's naturally not sandboxed. But interestingly, up until iOS 13, this NS unarchiver decoding actually also happened in Springboard. So with any NS unarchiving bug, you could like trigger it directly outside of the sandbox by targeting Springboard. And so we don't actually have to deal with any sandbox thing, because we can target Springboard. As of iOS 13, this has changed, and this one field that was being decoded in Springboard is now decoded in, I believe it's IMD persistence agent, but I'm not sure. But it is decoded in the sandbox process. Okay, this is where we are, pretty much done now. We have bypass ASLR, we have a way to deal with PAC by like chaining these Objective-C method calls together, and at the end we end up with a controlled call to this launch application with identifier. Of course we could do other things, but for demo purposes, this is of course what you do. So let me try to set up my demo. So 1 second. right, that's me. Not what I want. Okay. Nope. Actually, yes. Cool. So that's this iPhone here, just like screen captured with QuickTime. Let me see. So, this microphone is on, right? Yeah, perfect. Right. So it is on 12.4. It is a iPhone XS, so one with point authentication. 12.4 is the last vulnerable version, so that's like 9 months old by now, 8 months. Yeah, there's no existing chats. I don't know. Let's see. Is this big enough, by the way? I can increase font size. Last row, can you read this?
A little bigger, yeah.
Bigger. This is better?
Yeah.
Cool, thanks. Okay. So while this runs, I can maybe explain a bit what's going on. Yeah, so you see it's like doing this linear probing thing, like it's starting at the base address, checking if that's mapped. And now I hope you can read it. There, it does show these notifications popping up now. This is mostly, so there is a way to suppress those, but I think it's cooler if there's something showing up. Yeah, what else? So the way this works, it's using Frida. If some of you know this, like a hooking framework, and it's hooking into the Messages app on macOS, right? So, like what this is doing, it's using Apple script to send messages automatically, and then using a Frida hook to replace these messages with like my exploit content. Okay, so what happened now is it got a delivery receipt when testing this address hex1d000. And so it figured, okay, that's a valid address inside the shared cache. And now it figured how many possible base addresses are there that would lead to this address being valid. And now it's starting this basically binary search phase where it's roughly halving the number of candidates in every iteration. So it already went down to 17,000 from 34,000. Maybe another thing, it is like waiting roughly 10 seconds between each attempt, because if you crash too often, then the daemon will be like rate limited, right? So if you crash like 3 or 2 times within 10 seconds or so, then launch key will actually not immediately restart the process, but it will take some time. But yeah, so it just waits 10 seconds and then it's still pretty fast. Like it only takes 5 minutes. Anything else? Yeah. I guess this automatically restarting service problem is really like one of the key factors that makes this exploit possible. So if launchd wouldn't just automatically restart the service again and again and again, then this technique wouldn't really work. But yeah, launchd is very happy to just relaunch it every time. See, almost done.
Do you think Apple will add a mitigation to reduce gaming restart?
I hope so, but I haven't checked lately. It's kind of hard to test this, but this is one of my main recommendations. Yeah, this is also this same problem. It's not an Apple specific problem, right? It's like Chrome, also they also restart their processes frequently, so you can pull off similar exploits. But yeah, I do think it's pretty important to limit this. Okay, so this worked. So it's now saying, yeah, shared cache is mapped at this one address. And let's figure that out. I haven't stopped the time, but it can't have been that long. Yeah, if you're wondering why it says, if you're wondering why it says 941, this is some iOS thing. If you connect iOS to this QuickTime, it always puts the time to this. I think it's from some Apple demo where they put in this code. I don't know, but it is not recorded. Like it is actually happening here. Yeah. So this is now the heap spray that's going on. It is kind of hacky. So I think if you were to do this properly, you would do the entire heap spray in one message, which is possible. It's just more engineering effort. So I didn't do that. But I think that it would also be more reliable. So there is a small chance this crashes. So far, it has always worked during live demos, but we'll see. We'll see what happens this time. Okay, let's go. Yeah, it should be good. It's always freezing, like right before it works. Yes. Cool. Okay, yeah, thanks a lot. Yeah, I guess I can take questions now if there are any. Yeah.
So you mentioned that 12.4.1 they patched required this to reduce the issue. What was the fix in 12.4.1?
Right. So let me go back to my slides.
Repeat the question. Okay, repeat the question, Mike.
Yeah, sure. So the question was, I mentioned that Apple pushed some mitigation in 12.4.1. So what was this mitigation? So what I mentioned is when you use this NSKey unarchiver and you give it this whitelist, what actually happens is it will not just allow these classes, but also all their subclasses. So this is exactly the whitelist I had in iMessage, and it looks like it would only allow these 7 or so classes, but really it were like 50, right? And what Apple did is they exactly prevented this from happening in iMessage. So they put in a new decoding mode, like strict decoding or so, which now really just allows these 7 and not all the like 50 or so others. And all of the bugs we found, all of these, they were all in subclasses. And so they would not have worked anymore. Yeah, any other questions? Yeah. Mm. Mm-hmm. So I think the question, if I got it right, is if there's other NS-keyed unarchiver attack surfaces that we looked at besides iMessage, is that it? Yeah. So no, not really. This was focused on iMessage, so we only looked at the parts reachable like from iMessage, but it is absolutely correct. This keyed unarchiver is used heavily throughout iOS and macOS. It's used for like intra-process communication and inter-process communication. And so there's definitely more attack surface here. And also this mitigation that I mentioned, it seems to currently only be used in iMessage, right, and not in the other attack surfaces. Maybe they will also apply it there, but I, as far as I can tell, it's so far only there. So yeah, the answer is no, we haven't looked at any other users of this key unarchiver in that. Okay, cool. Well, thank you. If some more questions do come up, feel free to hit me up. I'll be around. And thanks for listening.